Okay, thank you everybody for being here. Thank you the people from home that are following us, and thank for the organizer for given me this opportunity. Okay, so the backdrop of this talk is the talk you have just seen. So, but if somebody falls asleep, I have doesn't work. Does it work? Okay, I have a cheat sheet like previously. So what are like the main things that we need for? So when lambda is a strong limit cardinal of cofinality omega, then you can do the descriptive set theory either in 2 lambda or lambda to the omega, or this weird sort of like PCF space, or even V lambda plus 1. And it's the same, so we can like switch from one space to the other, and it's all very fun. Many results in classical descriptive set theory hold also in this setting. And in general, the results that are dependent like to some tree structure or graph structure here works very well. While the more combinatorial ones usually work not very well. So A0 has an influence in this setting in the same way that AD has an influence on classical descriptive set theory. Okay, so this is the cheat sheet. Let's go from here. So we did the lambda PSP. The next step is, of course, silver dichotomy. This silver dichotomy is sort of like a perfect set property for coanalytic equivalence relations. So if we have a Polish space and a coanalytic equivalence relation on it, then either there are this equivalence relation has countably many classes at most, or you can embed 2 to the omega inside the classes. So like you have a perfect set of classes. So the question is, can we do this also in our new setting, in this new generalized descriptive set theory stuff? Okay, it's not true for the generalized Hilbert space. I googled it and I found this. I don't know if this is the first, but yeah, so it is not possible for if kappa is regular, but we are working on kappa singular, so maybe it's possible. So this is the theorem. Let's change things so that we have what we want. So first, let's change the space. Is this true? Maybe still not, because if you have this countably thing. So maybe with the lambda classes, still don't know if it's true. And this is true. This is a theorem. So if we have lambda, limit of measurable cardinals, strong limit and of cofinality omega, then and we pick a coanalytic equivalence relation, of course lambda coanalytic in this case, maybe I should have stressed this, then either it has lambda many classes or it has like a perfect set of classes. Okay, so where these measurable cardinals come from? Well, so one inspiration was a theorem by Scheller. Now, what theorem? So let me give some vague definition first. I would not say it's a definition. I still haven't decided the name of it. So let's pick an equivalence relation on some product space. I say that it has the singleton property. You can suggest other names. I don't know. If we pick two elements and they differ only in one coordinate, then they cannot be equivalent. This is a property. Do what you want. And Scheller proved in 1988 in a classical case that if E has this property, then we are in the second case of silver dichotomy. So there is a perfect set of classes. This is, I don't know how much is well known this, because it's in a paper that it's like completely outside this topic, but it's there. So actually Scheller managed to improve this to the generalized Hilbert space. And so, but starting with the lambda that is limit of measurable cardinals, then if E is a lambda coanalytic equivalence relation on this new space with this property, then again, second part of the silver dichotomy. So we have a perfect set of different classes. Perfect set of inequivalent elements. Okay. So, okay, this is the dichotomy, how to get to the first part. As I said, the things that here work very well are the things that comes from graphs and trees. So instead of looking at like the classical proof of stereo dichotomy, we try to see a different proof that uses graphs and passes through the G0 dichotomy. So what is the G0 dichotomy? G0 dichotomy is something classical. So let's fix a dense subset of 2D less than omega that intersects every level in exactly one element. And let's pick that couples two elements only if they start with the same element of S and they differ only in the next coordinate. So you have like they are the same until a certain point, something that is in S, then they differ, one is 1 and one is 0, and then they are the same above. So this is this is definition. Then I'm not sure about if this is the right paper. I think so. The theorem is that if we have an analytic directed graph on 2D omega, then exactly one of the following holds. Either there is actually Borel alpha 0 coloring of G, or there is a continuous function from 2D omega to itself that is a homomorphism, a graph homomorphism from G0 to G. And since G0 is quite complicated, I mean, this seems a lot like some silver dichotomy. Like this will give you that there are maximum alpha 0 classes. If this was injective, it would give you the silver dichotomy, but as it is, I think it is something. Okay. Actually, this generalizes quite nicely with almost the same proof. I mean, really mutatis mutandis. It's the same idea. It's just that since we are in a much more complicated space, the proof is more complicated to write down. But the idea is exactly the same. Maybe you need some tricks to get everything correctly. But the proof is almost the same. So what is the theorem here? Let's again find out. So first we change the space. Okay, so is this a theorem? No, I don't think so. There is still this alpha 0 coloring. No. What if we change the subset? So see, there we had a subset that intersects every level in one element. This is not dense in this new space. So let's put that intersects every level n in kappa n minus 1 elements, okay? Yes, sorry, it's lambda. Yes. So I like to call lambda singular cardinals and kappa regular cardinals, and so this time I changed and I forgot to change that one. And so let's pick a lambda coloring. Is this a theorem? Actually, we didn't manage to get this. This is a theorem. But we managed to do something a little bit more complicated, but that is at least equivalent for graphs that are the complement of an equivalence relation. I'm not sure, maybe it's equivalent. It's just like we can partition our space in lambda pieces, and inside any piece, you cannot have big completed subgraphs. I don't know if this implies that there is a lambda coloring. Maybe there are people here who knows better. But anyway, for our purposes, this is fine. And here you don't need measurable cardinals. This is just a theorem in CFC. Okay, so now what is more or less the proof? Like, I'm not going to the details. So let it be a coanalytic equivalence relation on our space. So its complement is going to be an analytic directed graph, and therefore by the G0 dichotomy, either it has less or equal the lambda equivalence classes, or there is this continuous function from this space to this space that is a homomorphism from G0 to G, and therefore picks elements from G0 and bring them to inequivalent element.
Wait, I thought you were just getting a homomorphism. You're getting more from the previous slide? Can we see the previous?
Yes. Oh, no, graph homomorphism.
So why did you write it in order?
Oh, sorry. I don't remember. No, it's not an infinite leaf. Like in the G0 dichotomy, it is an infinite leaf. No, so it's also here, it's not an infinite leaf. But yeah, it's not a problem. So the problem now that phi is possibly not injective. So classically, okay, from this point on, classically, we use the meager-comeager structure of 2D omega. We use bare properties and such to arrive to the silver dichotomy. But as Luca said before, we don't have here this. Like the meager-comeager structure, it's kind of nonsense in this setting. But then we can use, we cannot really use Sheller's theorem, but we can use the same idea behind this, because the complement of G0 has the singleton property. So we can use kind of similar argument to finally prove the silver dichotomy. So, okay, this is it, but I'm going to tell a little bit more. Let's look a bit into the future. So these are open problems. So can we get rid, first question of course is whether we can get rid of the measurable cardinals. Are they necessary or they're just there? I'm going to show you that this seems kind of necessary for this proof. Maybe there is another proof that is different. Also, I would say that, so these measurable cardinals are useful to bridge the part that in the classical case is bridged with the base structure, right? Meager, comeager, etc. So I'm just throwing this here. Maybe, I don't know, there is a way that we can use these measures to mimic something. Like, okay, you don't have meager, comeager, maybe we have something similar that works in the same way for, as in the classical case, I don't know. But, okay, more important to me, I was kind of a bit out of my comfort zone in the previous theorems because the consistency strength of the large cardinals was very low. Now let's get back to A0, and I feel much more comfortable. So one of the main points of the axiom of determinacy is that it generalizes regularity properties for all subsets of reals. Okay, so there is this theorem under determinacy that, like, you can have silver dichotomy for not just for coanalytic equivalence relations, but for all relations. It's kind of different. So you don't have that you have lambda classes, but you have that the classes are well ordered. But well, so in AD, oh, maybe this is wrong. Sorry, this is AD in L of R. So AD inside L of R, this is true. I think you cannot have this just with AD. Sorry, wrong. I wrote it wrongly. So either the classes of E are well ordered, or there is a perfect set of inequivalent elements. Is this true also in our case under A0? Question, I don't know, this is the open problem, but we have something close to this, very close. So I have two forbidden slides that I say, yeah, well, only if I have time. Well, I have some time. So a brief, yeah, I have 7 minutes, come on. So a brief summary of the proof of Sheller's result. So actually, so we have V.
Which one?
The first one I said. So that if no, okay, the second one. The one in the, it's the same, In the generalized descriptive set with measurable cardinals, yes. Yes. So, well, I can write it. So, if, let me know, right. So if E is like coanalytic and has the singleton property, then there is a perfect set of inequivalent elements. Now, I mean, this is the first theorem, just add lambda everywhere and you have the second with lambda limit of measurable cardinals. Okay, so what is the point here? We are considering the double diagonal Prickly forcing that has two Prickly sequences in lambda. This forcing has two important characteristics. So the first one is that if we have, so this is M, if we have a model, I mean a model of enough set theory, and I'm not going really into details here, then we can find the generics inside V. We can find some generics inside V. Also, another point is that only the tails of generic elements are meaningful. So if we pick generic, we change something at the beginning, we have something that is in the same model, like it's not really a new generic, it's something that is equiconstructible, etc. So I don't remember what I wrote here. Okay, so let me skip the first part, let me just go to the proof. So we pick a small model, okay, suppose there is a condition that says, okay, the two things that are in the generic are equivalent. Okay, pick this in V, we can, okay. Then pick another generic and just change one piece, okay. We just change one piece. This generic will still be in the extension, of course, but also since, I mean, the same condition will say that if these two are equivalent and these two are equivalent, it should prove, I mean, it's equivalence relation, also these two should be equivalent, but they're not because they differ only in one thing. So there is no condition that proves that the two generics are equivalent. So actually, all generics should be inequivalent, but there is a generic set of that, a perfect set of that. So all the generics of these things that are in V are inequivalent, and they are a perfect set. And okay, this is almost everything. It's just that, you know, they are inequivalent inside M of G. But the point is that since E is coanalytic, there is some absoluteness. I mean, once if in M there are all the reals, then I mean, saying that these two are inequivalent is the same in the M of G is the same as to say that these two are inequivalent in V. It's coanalytic. It's very easy. Okay, so this is pretty much the proof. I mean, you need to go into the details, but pretty much this is the proof. And it's kind of similar, like to, I mean, one of these ideas comes up in the zero dichotomy proof. The forcing is, I mean, you can use Gandy forcing or whatever. The difference here, why you need measurables cardinals, this is where I wanted to go. Why you need measurable cardinals? Because if you don't have measurable cardinals, then maybe you don't have generics inside V. Because if you just do something like Gandy forcing, but without the measurable cardinals, you are actually collapsing lambda to omega. And so all the generics are actually bijection between omega and lambda, so they're all outside V. And so, yes, you have a perfect set of inequivalent elements, but they're all outside V. So, yeah, nobody cares about that. All this to say that of the forcing of the space. So, if E is not coanalytic, much of the proof stays. we can get a little bit more using generic absoluteness. So under A0, suppose that all subset of E lambda plus 1 is representable, and then we have, I mean, the same theorem as Schella. So if we have an equivalence relation with the singleton property, then there is a continuous injection such that anyway, we have a perfect set of inequivalent elements. And that's it. Thanks for watching.